All right, let's get started. Appreciate you guys coming in today. I'm sure some of you want to go skiing, or maybe you're going skiing after this. But thank you for joining me. I get lonely without you. All right. Today's Wednesday, right? So Monday, we were talking about material properties and how this might be somewhat of a general review for you guys, but we're going to go through some very pertinent ones, continue to run through some very pertinent material properties with which we're going to use as we continue through this class. We're going to talk about material properties, and then we're going to talk about like design concepts, right? How do we take these material properties and utilize the stresses that we calculate, right, based on mechanics of materials in order to connect the two together, right, to come up with an adequate design. And what does that look like, and what do we consider, right? So we went through this tension test, right, the stress strain response for a material. We know we take a material, we put it into a testing machine or apparatus, we stretch it, right, we pull on it, we put load on it, we measure how much we are displacing it, right, so we can get strain or the intensity of the deformation, and then we can pull on it, right, with a known force, and knowing cross-sectional properties of the material, we can figure out stress, right, or the intensity of that force with which we're putting in the material. And we plot that behavior, I guess, the stress-strain response, right? And we get a curve, something like this, for something like steel or very ductile material, right? Something that undergoes a lot of permanent deformation, right? Anything beyond this yield point on the strain is permanent deformation, right? We're not going to get it all back. All we're going to get back is coming back down the elastic curve. So we talked for a second about if we do that, where we load up to a given point and then unload, right? This idea of we're going to be changing really the material properties of the material that we are testing. Right? Or in the real world, if you took a material and you brought it past yield, right, and then you unloaded it, we're changing the material properties, right? Now when we reload it, we get a higher yield stress, right? It's going to stay linear elastic further. It's going to have some permanent set, we would call it, or some permanent deformation in that bar, some amount of strain that we're never going to get back, unless we were to put it into compression, right? Then we'd have a stress strain response that does the exact same thing, just mirrored in both axes. So it's down here. So we have one property called the proportional limit. That's the stress where our stress strain curve is no longer linear, right? So the first time we load something up, it's going to be sitting right here at PL1. If we were to load it past our yield, right, or proportional limit, and then unload it, right, we've already gotten a new proportional limit. Right? We go to reload it, and the point where our stress strain curve is no longer linear is in a different spot, right? So we get PL2. Another method, or another parameter, you guys maybe have heard of. Have you guys heard of the 0.2% offset method, right? So the point at which our material yields, right? It's kind of hard to say exactly where this thing yields. So what do? Well, we just pick an offset of our stress strain linear curve, and we say that's where it yields. That stress strain offset when we do a 0.2% offset method. And that is a method to establish sigma y, right, or our yield of our material. And we do that. I can draw one in here. Might look something like this. Whoops, not like that. We're going to back up a second. Just going to draw this in. Might look something like that, where we draw a line that is parallel. Right, we have a slope E parallel to our initial linear stress strain response, right? This linear elastic portion. We offset it 0.2%. Well, we know that strain can be given in percent. So what does that mean? Well, it's 0.002 of strain. So we essentially just take our line, we offset at 0.002. in the hopes that we get outside of some of that transition region where we go from this linear elastic line to some sort of plastic line or on our material, right? Up here, it'd be the same thing. We'd essentially run a 2% offset, 0.002, and then we would read off what our yield stress is at that point, okay? So we can go through an example here real quick, okay? So in this case, we had a 100-inch long bar, and it's subjected to the loading pattern that we have here, okay? So we start out at 0, 0, right? Freshly manufactured bar. And we start pulling on it. We go up our linear elastic portion, right? We'll get to this point A. That's where we start to transition, right? It starts to keel over. We get into the yield range, right? We're yielding in that, or we have an inelastic strain. When we unload it, it comes right back down, right? That's the green line. Unload it, comes right back down the same slope as our linear elastic portion. We unload it all the way, it'll come all the way back to our x-axis. Then we decide to reload it, we go right back up, right? Follow it all the way back up until we meet that curve again. It starts to keel over, and we'll just continue to follow down the curve. And so they want to know what is the length of the rod before we reload it, and the proportional limit before and after loading. Right? So if we go for A, what's the length of the rod before reloading? Well, we know our original length, right? I guess we could start by saying we have our strain equation, right? Change in length over the original length. Knowing that, they gave us our original length, right? 100 inches. And they want to know what is the length of the rod before we reload it. So they want to know what's the length of the rod out here at this point on our x-axis, right? Well, out here on the x-axis, we know our strain. Know our original length. We know our strain, right? We could figure out what delta is, right? Delta, if we rearrange this equation, is the strain times the original length. So our change in length, right, is our strain. Well, our strain we can capture from our stress strain diagram. We're down here at, if I approximate that, I'm going to say we're at 0.005 inches per inch. Right, that's this point right here. Our original length is 100 inches. We get a delta of 0.55 inches, right? Or 100 times 0.005. Well, we know they're asking us for the length of the rod before we reload it. Well, that's the change in the length of the rod. So we merely have to add in, right, our total length equals our original length plus our change in length. So we get 100 plus 0.55. So before we reload, our rod is now, excuse me, 100.55 inches. We're going to call this strain 0.55, sorry. Any questions there? Pretty straightforward, right? Equation's fairly simple. We have strain, change in length over the original length. Figure out what we have and don't have. Finally, B, right? This one's fairly straightforward too, right? The proportional limit before and after loading? Well, the definition of proportional limit is where we change, right? Going from linear to non-linear in our stress strain diagram. So we might consider, I would consider those 2 points as being, the first one being A, right? If we started loading up, we're coming up linear elastic, right? That's when our elastic strain ends. So this point here is going to be our proportional limit at the beginning. Once we load it up to point B, right, and unload it, when we go to reload it, it's going to stay linear all the way until we hit the original curve, right? Well, that's going to be at point B. So we have our proportional limit before, which is point A, and our proportional limit after, which is point B. So we just need to pick off these 2 points off of our stress strain diagrams. So we have PL1, right? This is at A. I'm going to say that that's 43 KSI. And our proportional limit 2, which is at B, I'm going to say that's 60 KSI. So if you know the history of the strain that went into a material, right, you can determine changes in material properties. Right? Or you can do what's called cold working a material, where you purposely do this in order to make it a bit stronger. So you can change the material properties as you'd like. And for the application, okay? Let's go for another example where we're going to pull some more information off of a stress strain response curve. Okay, this is a stainless steel stress strain response curve. Okay, we started out with a 350 millimeter long bar. It's loaded in tension until it elongates 2 millimeters. Okay, so that would be our change in length, 2 millimeters. Original length, 350 millimeters. And then the load was removed. They asked us, what's the original yield stress using the 2% offset method? I think you guys understand that one pretty straightforward. What is the permanent set in the bar? What is the length of the unloaded bar? And if the bar is reloaded, what will be the new proportional limit? Well, if we look first, part A, they ask us for what's the original yield stress using the 2% offset method. Well, as we discussed, that 2% offset method is to just take that linear elastic curve, offset it to where it crosses the x-axis at 0.2%. So that means we're going to be sitting somewhere right here. Like that, right? That's actually really good, right? Damn. 2% offset method, right? Crosses the x-axis at 0.002. Follows the same slope as our linear elastic portion of the stress strain response. Wherever it crosses, somewhere in there, is our, what we would call our yield stress, sigma yield. I'm going to guess this at 440 megapascals. B asks us for what is the permanent set in the bar. Well, the permanent set in the bar after we reload it, right? The 350 millimeter long bar, that's the original length. We decided to pull on it to 2 millimeters. That's our change in length. And then the load is taken off of it, right? Well, we need to figure out how much strain we put in it originally, right? Because as we were loading this bar up, we are traveling along this curve. Right? We're just putting it in the testing machine, we're pulling on it, going up this curve. We know that we pulled it until we're at 2 millimeters. It was 350 millimeters, so we can figure out exactly where on the x-axis we pulled our material to. Right? Original length, 350 millimeters. Our change in length is 2 millimeters. We get a strain in our bar of delta over L. That's 2 over 350, 0.0057 millimeters per millimeter, or meters per meter, or inches per inch. All right. Well, we need to find where we're at on that curve. So we have effectively loaded this bar until we got to about here. Right? Load it till we got to about there. Then we unloaded it, right? And when we unload it, as we know, we come right back down parallel to our stress strain response, right? Our linear stress strain response of this initial part of our curve. So we come right back down, and we're gonna then end up down here at some strain. We'll call that the permanent strain, right? And we merely just read it off our curve. Something like that, right? That's how much deformation we've imposed into the bar. So then they ask, what is the length of the unloaded bar? Well, we know the original length of the bar, and we know now our permanent set strain in our bar. We can figure out how much that bar has elongated. 0.0035 times our original length is 350. We get a delta equal to 1.225 millimeters, okay? 1.225 millimeters is less than our 2 millimeters, right? Which is a good just kind of validity check, right? Take a step back and make sure things make sense. So 1.225 is less than 2, makes sense. Our permanent set in the bar, or permanent length, right? They want the length of the unloaded bar, is the length plus our deformation. So we get 351.225 millimeters, right? 350 plus our 1.225. So that's part C. Part D, just going back, if the bar is reloaded, what will be the proportional limit? Well, we unloaded it along this black line. If we reload it, we're going to reload it right back up that black line. And when we reload it, the proportional limit is the point at which our stress strain response becomes nonlinear, right? It's no longer straight. Well, it's going to be right when it hits that curve. So we really just want to see what is going on out there, right? This would be our proportional limit. Or in our case, I'm going to say it's 460 megapascals. Any questions? This is all review. All right, another quick example, right? What is the ultimate strength of this material? What is the yield stress of the material using the 2% offset method? And what is the modulus of elasticity of the material? So we get a stress strain response, right? This is the complete stress strain response. Okay. Obviously, this goes out to a very large strain, 0.12. Okay, that's way out there. So what we've done is they've blown up the initial linear portion, right? So we're only taking this out to 0.010. Right? So we're not even out to this first tick mark of this curve for the upper graph. All right, so we've taken essentially this portion of our stress strain response curve out. And blown that section up right there. What would you guys say the ultimate strength of the material is? Sigma U, based on that curve. There's no wrong answers, just guess something.
Almost 160.
Almost 160, yep. If you had to guess a number, what would it be?
158.
That's so wrong. I guess 155, but I'll give you 158. Oh, KSI. Got to make sure I reading the right units on my curve. What is the yield stress of the material using the 2% offset method? Right, well, we got to implement our 2% offset method. We're going to do something like this. Based on that, what do you think our yield stress is based on the 2% offset method?
Around 80.
80, yeah, exactly. That's what I guessed too. You're right.
I'm a little above 80.
Yeah, right. I guess we can get in there, huh? Shit.
81.
All right, 81 it is. If you wrote 80, you're wrong. Finally, last part here is, what is the modulus of elasticity of the material? Well, we know the elasticity of the material is really just our slope, right, of this, which is the same slope as this. So if we use our, right, E is the change in stress over the change in strain, right? Rise over run. Well, if we use the 0.002 offset method, we know that we're going to have some sort of change in stress over some change in strain. So what would be our change in stress here? We just had it, right? I gave it 81, right? We go from 0 stress, right, up to 81. Because you guys had to have 81 for some reason. Or 81 minus 0, right? That'd be the rise of that curve. The run of that curve landed somewhere there, right? So we're at 0.002 to 0.005. So we go 0.005 minus 0.002. All right, we traveled 0.003. Now I'm going to have to recalculate this because you guys use different numbers. 0.003. E equals 27,000 KSI. Right, and that's part C. It's merely the rise over the run. You could have picked a different point on this graph here. Okay, we could have picked right at the end of this linear portion, right, where we were at, say, 60 KSI, and we were at 0.002. We should have gotten something very similar, probably right around 30,000 KSI. All right, I'm going to skip that page because I duplicated it for some reason. All right, I mentioned this idea of Poisson's ratio a little bit ago. Maybe you guys have addressed this in the materials class a little bit, right? It was this idea that if you start stretching something, right, in one direction, that there's going to be some stretching going on in the perpendicular direction. Right? That piece of rebar I was handing out, which I don't know where it ended up. Does anybody see it out there?
They're behind you on the ground.
Oh, wow. They really hit it, didn't they? Way to spy that. Damn. That's impressive. Right, as we pulled on this rebar in the lab, it's getting longer in the longitudinal direction, but it's also getting shorter in the radial direction, right, or the diameter direction. And Poisson's ratio, the equation of which is minus what we would call our lateral strain, right? The perpendicular strain from the direction of loading over the longitudinal strain. So if we looked at this, right, we're talking the lateral strain being perpendicular.
What's that thing?
What's what thing?
On the left side of the equation.
Oh, mu? It's a Greek symbol?
Use uppercase of mu.
What's that? What's that?
Never mind.
What is that? Did I do something wrong? It might not be. My Greek symbols are pretty bad, right? It's a Greek symbol. I'll tell you that with confidence. Okay.
It looks like a check mark.
What's that?
It looks like a check mark.
I guess it is, isn't it? Can I draw it something better than this? That? That still looks like a check mark, huh? It's a Greek symbol, okay? Greek. Just say Greek, which is Poisson's ratio, okay? Is the negative lateral strain over the longitudinal strain. Right? It gives us this behavior of what's going on in the lateral direction versus the longitudinal direction when we pull on something, we stretch on something, right? When you pull on a bar, right, we're adding stress. The bar elongates. Right, we have, in this case, a longitudinal strain. While this idea of Poisson's ratio is a quantification of the fact that the bar also contracts. In cross section. This is our lateral strain, right? And it's negative because if you're pulling on something, right, with a positive longitudinal strain, right? We know that positive strain is in tension, right? It's pulling, is elongating something. And that means in the lateral direction, it's actually getting smaller, right? It's a compressive strain. It's getting smaller in diameter or smaller in cross section. Most of the time, I don't want to draw the symbol now. You guys are making me so self-conscious. All right. Poisson's ratio, or Greek, right? That Greek symbol equals usually 0.25 to 0.33. Steel's 0.3. Okay. So depending on the material, here I'm going to do it. Boom. What's that? Our largest possible ratio that we get whoops, 0.5. Do you know what material that is?
Rubber.
Yay, crushed it. All right, rubber, that's exactly it, right? Very, very good at conservation of mass going in one direction versus the other, right? Pull on it, it's going to contract. This is rubber. Man, you guys surprise me every day. All right, well, why is this important? Well, it's important because as engineers and designers, right, if we are pushing or pulling on some material, right, we need to make sure that the deformations that we create in the lateral direction either serve our purpose, which we'll look through an example of one that would serve a purpose, or aren't detrimental to the design as a whole, right? If we were putting like a bar through a sleeve and then we decided to put that bar in compression, right? Depending on what's going on with the sleeve, we wouldn't want to push the bar so hard that it expanded and broke the sleeve, right? Or if it was a bearing and it was trying to align a bar, right, that was going through the bearing, if that bar we decided to put in tension while we were twisting it or something, right, and rotating it, there's a point at which we could pull it so hard that it no longer has good enough tolerances with the bearing, and that bearing is no longer going to be keeping that bar in alignment, right? There's going to be some play in that bar. So why important? Knowing our longitudinal strain we can calculate our lateral strain, or really the expansion and contraction of elements. Right? Expansion of rods and compression is a big one. Right? So we have this idea of the elastic modulus of elasticity, right? Have you guys talked in your materials classes about the shear modulus? Okay. Very similar, right? The elastic modulus, Young's modulus, is our normal stress over our normal strain, right? Well, our shear modulus is our shear stress over our shear strain, right? This comes into play later on in the class when we start talking about torsion, because we put things into shear stress and we look at shear strain of torsional rods or rods in torsion. Well, there's a cool relationship between our Young's modulus and our Greek symbol. Okay, that's what that is right here, Greek symbol. New? So the shear modulus G is essentially our shear stiffness, right? Our Young's modulus, or elastic modulus, right, is the stiffness of our material loading it in the axial direction, right? If we push and pull on it like a spring, what's its stiffness? Well, that stiffness is E. Well, if we were to twist a shaft, right, the stiffness of that shaft with respect to twist is what we would call our shear modulus, and that's G. And that shear modulus, whoops, is a function of Young's modulus and the Poisson's ratio for our material. Let's do a real world example here, right? Pretty real world, I guess. Anybody here used a Dremel? Yeah? A couple of you? Right? Dremel is just an electric tool, right, that spins a chuck. It's like a drill, okay? And then at the end of the drill, you put a bunch of these little fittings on it, right? So you can do really fine work. Okay? Sometimes what you put in the drill, in the chuck of the drill, is this sanding drum. Okay? Maybe some of you guys have seen them. Well, these sanding drums, right? A consumable, something that we would replace often, right, would be the sanding sleeve, which would slide over. This, in our case, is a rubber mandrel. So you would loosen our bolt, right, our nut on the end. That would contract our rubber, right, allowing the sleeve to be pulled off. You put the sleeve back on, you tighten this nut back up, right? And we're putting in, the nut is putting in longitudinal strain into our mandrel. We're squishing it in the longitudinal direction. As we know from Poisson's ratio, right, we're going to have a lateral strain. And that lateral strain, because we're putting it into compression, a negative longitudinal strain, we're going to get a positive lateral strain. So that rubber is going to be pushing against our sanding sleeve and allow it to grip it so that we can use it in our Dremel tool, okay? So what do they tell us? Well, they tell us all sorts of shit about this thing, right? Everything we need, nothing we don't. And that's how example problems work, right? Well, they tell us it's 3 inches long, okay? They tell us the diameter, original diameter, was 2 inches. Our final diameter is 2.15 inches, right? If anyone's used a Dremel, I know you guys are out there measuring that, right? Like, all right, I'm gonna just keep measuring it, make sure I get to 2.15 inches. That'll hold this sanding sleeve good enough, right? And they ask us for the average normal strain along a diameter of the mandrel, okay? The circumferential strain at the outside surface of the mandrel, and the Poisson's ratio if the compression along the length of the material is 0.45 inches. What does that mean? Well, that means that somebody decided to tighten that nut, and when they tighten that nut, they shortened this thing by 0.45 inches. Seems pretty excessive, right? If you had a 3-inch long mandrel, you're going to tighten that thing until it's squished up half an inch. It seems a lot, but we'll let that slide, I guess. So we start at A, the average normal strain along a diameter of the mandrel. What is our strain equation? Strain is change in length over the original length, right? Delta over L. No tricks there. Well, if they're asking for the normal strain along the diameter, right, we're looking at this with respect to the change in length over the original length of the diameter of the mandrel. So we want really the change in the diameter, right, over the original diameter. Well, they gave us our original diameter and our final diameter. So if we do our final minus our original all over our original, that would give us our normal strain along the diameter, right? Epsilon. We'd get a epsilon of 0.075 inches per inch, right? Meters per meter, feet per feet. It's all the same. B, what's the circumferential strain at the outside surface of the mandrel? Well, now instead of going with respect to our diameter, we're going to do it with respect to circumference. What's the equation of the circumference of a circle? No judgment here, okay? This is a safe space, right? We've all introduced each other. All you gotta do is just say something, right? 2 pi r. So what's that with respect to diameter? Wasn't a trick question. I'm not trying to. Right, so 2 pi r. What's that with respect to the diameter? Maybe just pi d, right? 2r. Nothing tricky there, right? 2r pi d. So circumference. This is a safe space. Right. So our strain with respect to the circumference. Nothing tricky here. Same equation with respect to strain, right? So now we have now we want our change in the circumference over our original circumference. I'll call it C naught. What does that equal? Well, we knew our original diameter, or our final diameter is 2.15. Well, we need to now multiply that by pi to get our final circumference. Then we're going to subtract our original circumference, which is our original diameter times pi. We're going to divide it by 2 pi. All of our pi's cancel out. Get the exact same thing. Right? Because there's a constant scalar between diameter and circumference. The strain is the exact same thing. So we've got our circumferential strain and our diameter strain. Last thing to ask is, what's the Poisson's ratio if the compression along the length of the mandrel is 0.45 inches? Now this is when you guys get to make fun of me again. We got that guy minus our lateral strain divided by our longitudinal strain. Okay. Well, we have our lateral strain, right? That's this guy up here. Right? That's our change in strain in the lateral direction. And then we have our longitudinal strain. Well, we haven't calculated that yet. Right? We need to figure that out. Well, strain is the change in length over the original length. We can calculate that pretty easily. So let's start down here. We're going to say, well, that's a terrible epsilon. Equals delta over L, as it always is. Well, of course, right, being an example problem, they gave this to us very straightforward. Like they said that someone's going to tighten this down to the point where the length, which originally started at 3 inches, squishes by 0.45 inches. So we have our original length, right, and our change in length. We can just plug those things in. 0.45 divided by 3. That is one thing to note here, right? Our change in length is a negative value because it got smaller, right? So we've got negative 0.15 inches per inch. Well, we can now plug that in up there. So now we get negative 0.075 inches per inch divided by negative 0.15, we get 0.5. And as we mentioned in the last slide, right, rubber is 0.5. So every 1 unit of strain in the longitudinal direction, we get half that unit in the lateral direction. Okay. Any questions? Okay. Well, in 3.3 of the text, they talk about this idea of Hooke's law. You guys know what Hooke's law is, right? It comes back from the stress-strain response. It's that relationship between stress and strain, which is our modulus of elasticity. So from stress strain more importantly, the linear portion we got this relationship that stated that our modulus of elasticity E was sigma over epsilon, right? Which was our stress over strain. Well, this relationship, strain equal to, whoa, keep wanting to write, stress over E, or stress equals E times strain. This is what we would call good old Hooke's law. It's a constitutive relationship. It's relating deformation to stress. Okay? As you can imagine, with materials, this only works when you're in that linear elastic portion, right? Which for some materials, that's all they're ever in, is the linear elastic portion. Any ideas of a material that only stays in the linear elastic portion? And then it breaks, might shatter? Glass, like ceramics, right? You drop your plate or your bowl and it shatters, right? It doesn't just fall on the floor and go flat. Right? Ceramics are very brittle materials, right? They don't get any permanent deformation. And so they really follow Hooke's law, right? The stress strain response. But like steel or plastic, some of those things that get permanent deformation, they follow Hooke's law on that linear elastic portion. The second you get out there, this behavior doesn't match, right? You got to come up with a new, what we would call constitutive relationship, which relates strain to stress. But for a lot of materials, this is what we deal with. So stress equals change in stress over the change in strain times strain, right? It's essentially taking one of our Hooke's law equations here, right? Sigma equals E epsilon. Well, that's what this is essentially boiled down to, right? Raw data. All right, save the best for last here, okay? Now that we know Hooke's law, you guys know the strain relationship, right? Definition of strain and the definition of stress. We can take all of those things, put it all together, and we can relate forces to geometry and material properties. What is our basic equation for stress? Something over something. What is it? Force over area, right? So we have F over A. Strain, epsilon. What's that? Yeah, change in length over the original length. Call it delta over L. Finally, we just learned this. Hooke's law. What's strain with respect to Hooke's law? It's written right up there. You just can't see it. You guys should have it on your notes. Yes. Stress over the modulus of elasticity. What can we do here? Well, we can do this, right? We can plug this in. We can say the stress over the modulus of elasticity is the change in deformation over the length. So now we get, right, sigma over modulus, it's change in length over the original length. Well, now we can plug in stress, right, force over area into that portion. What does that mean? Well, that means we get this equation that says F over AE equals change in length over the original length. We're going to rearrange this one last time and say that the change in length is the force times the length over the area times our modulus of elasticity. Right? We can directly relate now deformation to loading, geometry, and our modulus of elasticity. Right? This will become incredibly useful in the next, shortly in this class when we start talking about axial deformation of members. And we can figure out just that based on the applied load, what the geometry of our element is, right? And what are the material properties. All right. Have fun skiing if you're heading out.